Okay, so we will proceed with your Unit 3 and then Unit 4. Okay, so we will combine these two units in a single discussion of your Module 2. Okay, simple strain still. So in Unit 3, we will now be discussing with what is axial deformation, and in Unit 4 is shearing deformation. We will combine these two. So this is the unit learning outcome for Unit 3 and 4. Okay, so use the principle of deformation to solve for problems in mechanics of deformable bodies. So we will now to apply the relationships that we discussed on the previous unit 1 and 2. Okay, stress and then strain. So axial deformation, if we say axial deformation, that is due to axial stress. Okay, so again we derive this one, or we discuss how this is derived before, or how this relates with each other. So that is your Hooke's law. So a convenient variation of Hooke's law is obtained by replacing your sigma, or yes, this is sigma by its equivalent P over A, isn't it? Your sigma is the axial stress, which is the axial force over, or the force over the area receiving, and replacing the epsilon by the deformation over the length. Okay, so that instead of solving first for the stress and then solving for strain before relating these two, then we can actually establish a relationship between the force and deformation by breaking down the values of the sigma and epsilon. Okay, so changing the sigma into P over A, and then the epsilon by this epsilon by delta over L, then we can play around so that we can establish the formula of direct solving for the deformation, axial deformation, to be PL over AE, wherein your P is the applied load perpendicular to the area, which is your A, and then the L is the original length, and then your E is the Young's modulus, or the modulus of elasticity. So that is for axial deformation. For shearing deformation, we will be using the shear stress, okay, which is by the way, this is not established before. We did not discuss this one before, but as the same as your Young's modulus, we have this what we call as the modulus of rigidity. Okay, modulus of rigidity, which is relating the shear stress with your shear deformation. Okay, which is your gamma. Okay, shear strain. Shear strain, which is your gamma. So playing around with this, your J is the ratio of the shear stress with your shear strain. Okay, gamma. And then you can actually break this down. Okay, we can break this down just like what we did here in your axial deformation, or in your shear stress is to be broke down into shear force V over A, and then your deformation gamma, we can break this down into strain gamma, okay, into deformation sub S over L. So that we're playing around with that, your shear deformation. Okay, so to differentiate that one with the axial deformation, let's write down that sub S. Okay, that will be VL over AG. In here, PL over AE, because the ratio of stress and strain is your E, Young's modulus E, axial strain. Okay, the ratio of the shear stress with the shear strain is your J, which is your modulus of rigidity. Okay, so these are the formulas of direct solving for axial deformation and shearing deformations. So let's have an example. So it says there that a short post constructed from a hollow cylindrical circular tube of aluminum, okay, supports a compressive load 250 kilonewton, which is in this figure. So that is hollow, inside is a space. The inner and outer diameter of the tube is 9 and then 13. Respectively, and the length of that is 100 centimeters. So that is just a short column. Okay, 100 centimeter is equivalent to 1 meter. Okay, so that's only 1 meter. And then the shortening of post due to the load is measured to be 0.5 mm. So look at that, 0.5 millimeter compared to 1 meter or 100 centimeter. So that is very, very small. So the deformations are very, very small. So actually, if you will try to notice that one, that is not visible to the human eye. Okay, so determine the compressive stress and strain in the post. So disregard the weight of the post itself. Assume that the post does not buckle under the load. So we will try to assume that this will just resist the 250 kilonewton. So forgetting about the weight of this, the self weight of the column, But in the actual scenario or the actual designs, we are actually considering that one. But for simplicity, since we are still on the simple analysis, let's forget first about that self weight. And actually, let's consider that is still intact, okay, to carry that 250 kilonewton. So it will not buckle. So given, write down the P there is 250, which is compressive. We need to take note of that. And then uh, we have here your what to call this one, diameter, inside diameter 9 centimeter, and then 13, which is the outside, and then the deformation, which is 0.5 millimeter. And then the required is the stress and the strain. So compressive stress, okay, by the way, I did not include here the sign, but in case you have there a mixture of axial and compression, it is better for you to include the sign convention, wherein the compression is negative and the tension is positive, together with the strain, okay, wherein the compressive strain is negative because that is shortening, and then the tensile strain is positive since that is elongation. If there is a combination of that, so that you can differentiate, okay, if you will combine these two. But since this is just a compressive, then actually I can just consider that as positive. But I need to bear in mind that that is compression, okay. So compressive stress is force over area. So what is our area? Area of the outside minus the area of the space inside. So area of the big. So that is just simplified. Okay, pi d squared over 4, and then pi d squared over 4. We can factor out pi over 4 since that is a constant. So d of the outer minus d squared of the outer minus d squared of the inner. So that's our area. Or if you will try to solve that one, I want to put that in millimeters. Okay, so that I will put the force in Newton, so that I will end up with megapascal. So the area, I want to make use of the entire value, so 2200 pi millimeter squared. And then that is your area, and then your force, multiply that one to 10 raised to 3 to make that as Newton, so that calculating this will be 36.17 megapascal or Newton per millimeter squared. Okay, so that is our stress. For the strain, that okay, so that is the deformation over length, and then deformation is just 0.5 millimeter, and then the length I need to put that in millimeter. Okay, so that 100 centimeter times 10 to make it millimeter is 1000. So that will be 0.0005 okay, millimeter per millimeter, or simply that is unitless. So that is our strain, and then this is our stress. So actually, given this scenario, we can compute actually for Young's modulus, wherein Young's modulus is stress over strain. So you can divide this one, but I did not include here. So you can figure out actually, basing on this, let's say that this is in its elastic stage, still elastic stage. So we can figure out the Young's modulus E. So if you want to do that, then you can just solve that one. E is the ratio of stress over strain, so 36.17 divided by 0.0005, so you will end up here with 72,340, which is megapascal. Okay, so for this certain type of material, which is aluminum, you can say that that has a Young's modulus or modulus of elasticity to be 72,340 megapascal. Okay. So that is for example number 1. So let's try to have your number 2. An aluminum bar having a cross-sectional area of 0.5 square inch, okay, so that is supposedly square inch, okay, carries the axial load applied at a position shown. So this is a composite loading, okay, so at a certain cross-section the loading are different. So compute the total change in length of the bar if E, or the modulus, is 10 times 10 raised to 6. That is 10 raised to 6. Okay, 10 raised to 6. Let me just change that one. Okay, let's just change that one. So that is inch squared. So how will I write that one? Okay, let me just write that as raised to 2. And that is 10 raised to 3 also. It is altered when I copy the value. Okay, so that's it. So your Young's modulus for this certain type of material, which is aluminum, is 10 times 10 raised to 3 psi. So that is pounds per square inch. So assume the bar is suitably braced to prevent lateral buckling. Okay. So assume na compact yung section given this type of loading. So hindi mag-affect yung movement niya sa stress, okay? Or sa behavior ng material natin. So if I will try to cut here, let's try to figure out, let's say that is P1, what will be our internal reaction, okay, that is experienced within this section. So that is equivalent, okay, summation, you will have this going to the right as P1, 600 pound, that is tensile, okay. If I will cut within this middle section, that will be, okay, if I will summate, this is going to the right and an additional going to the, I mean left, and additional going to the right, which is 6,000 and then 7,000. If I will get the resultant of that, will be going to the right, which is 1,000. So therefore, that is the reaction, okay, internal reaction 1,000, which is going to the left, which is tend to be going directly to the material, so that is compression, okay, compression. And then on the last part, I will cut it here, so summation. So going to the right, which is 7,000, and then a total of going to the left, 6,000 plus 5 will be 11. So 11 minus 7 will be 4, which is resultant going to the right. Therefore, the reaction will be going to the, I mean left yun. This is now reaction going to the right, which is 4,000. Okay, the summation or the resultant of this, which is going to the left, will be counteracted by going to the right, which will tend to elongate, which is tension. Okay, so those are our given. The areas are constant, so 0.5 square inch. Okay, 0.5 square inch. The material is single, so aluminum, which is E, which is the same in all throughout, but the only difference is the loading with the cross section. So length of that is 3, the middle is 5, the last is 4 feet. So convert that one in inch, multiply the feet into 12, so that will be inch. So 36 inch, 60 inch, and then 48 inch. So these are our dimensions, and then forces within a given cross section. And then what is being asked is to find the total change in length, or that is the total axial deformation. Okay, total axial deformation. Axial because the stress are axial. Okay, compressive and tensile stress, since the areas are perpendicular to the forces. So let's try to check the unit, okay, just to be sure that we have here the right unit for that to cancel out. So okay, actually you do not need to show this one, but I will just be showing this in order for us to understand what will happen. Okay, so for deformation formula, PL over AE, we established this one before in the previous slide. Our P there is in pound. Okay, so we'll go, so that is pound, and then our length is in I transform that one in inches, and then our area is inches squared. Okay, our E, or the modulus, is PSI, pounds per square inch. Okay, pounds per square inch. So what happens? Inch squared cancels, pound cancels, so we will end up with a deformation of inch. Okay, so we can now use directly the formula that we established, that PL over AE. So we will start with this first, okay, due to the first cross section, second cross section, and the third cross section, and summate all of that, and then you will end up with the total deformation. But you need to consider, since look at this, it is a combination of tension and compression. So we need to follow now is sign convention, wherein a tension is positive, a compression, because compression tends to reduce the size. So let's put that as negative. So compression is negative. So the deformation for P2 is negative. So I put that as minus. For the tension to be positive. So PL over AE. So for the first cross section, P there is 6,000. The L there is 36. Length one is 36. Area is 0.5. And then that E is 10 times 10 raised to 6. And your second cross section, okay, that is minus, since that is a compression, okay, resultant is compression. The P there is 1,000, okay, 1,000 compression. The length is 60 inches, and then the area is the same, and then the E is the same. So actually we can factor out that A times E outside, okay, if you want. And then in your third cross section, that is 4,000, the P is 4,000, the length is 48, and the area and then E is constant, okay. So calculating for all of these, you can combine that one. So that will end up with positive 0.06 90696, or that is 0.07. You can say that it's 0.07 inches. That is positive. It means that it will elongate. Okay. But if that will end up negative, then it means that will shorten. Okay. So let me just recheck that one. Okay. You can just you can recheck that one. I will factor out 1 over AE for in 0.5 times 10 raised to 6. And then inside is 6,000 times 36 minus 1,000 times 60 plus 4,000 times 48. That will give us 0.0696. Okay, so we are good. So that is our total deformation. Okay, so that is the total deformation of your bar. Okay, so that's it. Let's have another example, one more example. So this is now a little bit complicated, but this is actually just analysis of the system, relating that one with your deformation and stresses. Okay, so this rigid bar ABC, so it says they're rigid. Okay, so even if you will try to undergo the loading with the system within the loading P, this is assumed to be still straight, so that will not bend since we assume that one to be rigid. Okay, so even if you load that one by P, this will not bend, rather that will just be this deformation. Okay, so in this figure, okay, wherein that is hinged at A, so that is free to rotate, and then supported by a steel rod at B. Okay, so that is a steel rod, and then determine the largest load P that can be applied at C. So let's figure out that maximum P to be applied at this point C. If the stress in the steel rod, okay, this is your steel rod, is limited only to 30 ksi. So look at this, we are now combining the stress and then the strain. Okay, so limited only to 30 kips per square inch, and then the vertical movement at C, or that is yes, the displacement at C is limited supposedly to 0.1 inch only. It will not exceed 0.1 inch. Okay, so that is our scenario. So first, let's try to. There are two given to satisfy. We should not exceed that 30 ksi, and we should not exceed that 0.10 displacement at point C. So first, let's try to figure out, satisfy first that limitation 30 ksi. Let's figure out what is the P for us not to exceed that 30 ksi. And then later on, let's try to find the P so that we will not exceed that 0.10 inches in your displacement at C. So let's consider first your KSI, 30 KSI. So relating this one, so if I will try to figure out this force, that the internal force that is being resisted by this steel bar, okay, in relation to your force P, since of course we cannot solve the equivalent value of the reaction since the P is the unknown. So we will be finding the reaction at the steel bar in relation, okay, as a value of P, as a value of P. So if I want to do that, I can cut this one so that I will expose that one to be in tension, because obviously that is under tension since that is your force P going down. So if I will try to take a moment for me to cancel, okay, for me to cancel the reactions at A, so that I will only expose the reaction at your steel bar. I will get a moment at A, okay, get a moment at A. I will consider clockwise to be positive. So clockwise is positive. What is the clockwise here? Is the product of P, force P, times 2 plus 4, plus 3, which is 5. Okay, that is positive. And a negative for the moment of your reaction of the steel bar, which is negative since that is counterclockwise, times 2. So that's it. That should be 0 for that to be in equilibrium. So rearranging this one, then that is 2P sub ST means this is for this steel bar. And then P is the unknown P, which is 5. And then cross multiplying that below, so you will end up with 5 divided by 2, or that is 2.5P. Therefore, the reaction at the steel bar is equivalent to 2 times the 2.5 times the P. Okay, so if you know that P, then the reaction at the PST is just multiply that one by 2.5. And then we will now try to make use of that limitation 30 KSI. So we will not try to exceed. So let's say I will equate that one. We will maximize that 30 kips per square inch. Then what is that again? That is the stress, allowable stress. So what is stress? Stress is force over area. So what is our force? That is the reaction, the internal reaction of your steel bar, which is PST over the area of that. Okay, what is the area of that? It is given here to be 0.5 square inch. So, okay, given yung stress, limited stress, given yung area natin, the unknown is P. So, playing around with this, inches squared will cancel. So, this will go down, this will go up. So, you can check that one. 30 times 0.5, 30 times 30 times 0.5, divide this one by 2.5, will end up with 6, exactly 6 kips. Okay, inches squared will cancel, so we'll end up with kips. So that is the P for us to attain that 30 KSI in your steel bar. Okay, so that is the limited P. It means that we can only reach up to 6 kips for the loading of P for us not to exceed that 30 KSI in your steel bar. Okay, for us, we need to satisfy also the scenario wherein that should be only up to 0.10 inch. The displacement at your point C should be up to 0.10 inch only. So how is that? Look at this. Since we assume again that that is rigid bar, so if I will try to load that P, then this will elongate. This is allowed to elongate. Okay, this is allowed to elongate. Then if that will elongate, then this will be the elongation, isn't it? If that will elongate, for that to be in this form, then there should be that elongation. Okay, so we will limit that one to 0.10. That displacement at point C to be 0.10. And then by ratio and proportion, this is just a right triangle. Okay, this is just a right triangle. So by ratio and proportion, then the deflection delta ST, okay, that is axial deformation. That is the deformation of our steel bar. Over 2, that is the ratio of the delta ST with the length, which is 2, is equal to the ratio of the total deformation, which is our limitation 0.1 inches, with the length, which is 2 plus 3, which is 5. So playing around with this ratio and proportion, okay, this is a ratio and proportion, this will go there. So 0.2 over 5, or that will be 0.04 inch, okay. So that should be our deformation, axial deformation of the steel bar. So if that is the axial deformation, what force, okay, what force P will give us a 0.04 deformation of your steel bar? Okay, so again, using now relating your deformation with the force, and then with the length, and then with the property of our steel bar, so that is your PL over AE. So P there is the internal reaction, or the internal force encountered by the steel bar. L is the length of the steel bar, which is 4 feet. The area of that is 0.5 square inch, and the E of that, modulus of that, is 29 times 10 raised to 6 PSI. Okay, so substituting that one, but do not forget what we are trying to find is not PST. Since this is already there, that is given, this is given, this is given, the unknown actually is your P sub ST. Okay, that is the reaction of your steel bar, but that is not the unknown in the problem. The unknown in the problem is the force P, the maximum force P. So we will try to substitute that by its equivalent. Isn't it? We figured that out a while ago by getting a moment at point A. So that PST is equivalent to 2.5 P, then we can change that one to 2.5 P. Then substitute what is given. So length is 4 feet. Convert that one to inches. So multiply that one by 12. Area is in inches squared, 0.5, and then the Young's modulus is pound per inch squared. Playing around with this, inch squared cancels, inch and inch cancels, pound will go there on the other side, so you will end up with a P, which is pound. Okay, we can recheck this one again. 0.04 times 0.5 times 29 times 10 raised to 6 over 2.5 times 4 times 12. And you will end up here with 4833.33. Okay, 3333, or that is pound. Okay, this is in pound. So for us to compare this one with the force P that we solve here, we can convert that one in kips, or again, 1 kip is 1,000 pound. So just move that one to 3 decimal place. That is 4.8 kips. Okay, 4.833 kips. So what does that mean? Okay, in our first scenario, when we maximize the strength of the steel bar, that can carry up to the value of P to be 6 kips, for that not to exceed the 30 KSI. For the second scenario, for us not to exceed that 0.10 displacement at point C, that should only carry up to 4.8 P. Therefore, what is the answer? Okay, what is the answer in our problem? What is the maximum P for us to satisfy these two scenarios? Is the smallest, which is 4.8. That is the same as our examples before. Choose the smallest since we are referring here to the limits. So that is for example number 3. Okay, so this is now a mixture of deformation and stresses. So for this unit 2 and 3, 3 and 4, axial deformation and shear deformation. So are the important concepts. So tension produces elongation, so positive. Meanwhile, compression produces contraction or shortening, so that is a negative deformation. And then perform unit check before you compute the final answer. Make sure your units are consistent. But if you are solving this one in this manner, wherein all you need to do is carry the unit for you to see the cancellation, you do not need to do the unit check. But if you are solving this one by directly substituting the values without analyzing the unit, you need to do unit check. Okay. So again, if you have any question in this, we will be discussing in the live meeting, or you can comment that one on below the video. Okay, so thank you very much for watching.